Hi class, we're beginning chapter 4 and we're going to start with 4.1, the electromagnetic spectrum. So we're going to look at light and the colors that are visible to us along with other parts of electromagnetic spectrum. The light that is produced is connected to atomic structure and the way the electrons are configured around the nucleus. So that's how we're going to start with not looking just as light, but what is causing the light and how it's causing the light. So what is light? Light is a type of electromagnetic radiation. If you don't know what that is, you will on the next slide. Electromagnetic radiation is energy that travels as a wave, and these are produced from charged particles. These waves are made up of these small energy packets called photons. And think of a photon as a small packet of light, if you will. So here's the electromagnetic spectrum, and there's a lot of information going on here. First, let's take a look at the arrow. It starts at a low frequency, low wavelength. What does that mean? That means low energy, because here's the energy. And then when we get to this side, it's high energy. So what would be considered items that are low energy? Well, we start around TV, radio. These are in nanometers, and we will cover, meters, and then this is in nanometers here, and I'll cover that. So if you're looking at the lower end of the spectrum here in meters, we have TV and radio, part of the TV and radio waves. Then it moves up to higher energy of microwave. Then it goes to infrared. And then we have a small kind of sliver that's visible. And if you can notice, it is the rainbow colors. And we'll cover that in a little bit, but I just want to, we'll jump back to that. Then UV, X-rays, and the highest energy is gamma rays. This has the highest frequency and the shortest wavelength, and I'll cover what that means. But let's jump back to visible. So when we see colors of light, you may not have been aware that there's actually numbers attached to those colors. These are like a fingerprint. Red tends to be in the 600 to 700 nanometer range, so you will never see blue in the 600 and 700 nanometer range. That number is an address for that color, and it's only for that color. So these again are like fingerprints. So lowest energy in the visible is in the red, very dark red. And over here, I know this color doesn't show it here, but you can kind of see it goes violet and purple, and then it just goes really dark. It's very interesting because if you do a Google on any of this stuff, you'll see that the colors are generally the rainbow colors, but you'll see some that actually show it really purple, and then others are like this. So it's chemistry is supposed to be straight across the board, but there's these little interesting things. So this is one of the things that we're going to look at. So here is a slide from one of my other courses. This one gives it spreads it out more, and it calls low energy. So on this one is low frequency, long wavelength, but you don't see the wavelengths. This is high frequency, short wavelength. On this one, you see the wavelength, and it allows you to understand, and then we spread out here. And another thing I want to point out, and it'll come up again, you see how this one starts at a red at 750, and this is violet, where now you can actually see a color of violet. This one in your book ends at 700, and this goes to 350. That's one of those weird inconsistencies also in chemistry where the numbers are slightly off. Your book wants it with these numbers, so I would go by these numbers, but this is a slide from another book. I just want you to see the wavelength and how everything is, and this also shows violet, which is nice to actually see the color violet. Okay, so the entire electromagnetic spectrum has short wavelength, high frequency radiation on the right, and long wavelength, low frequency on the left. Visible light is a small sliver. So this starts at the low energy, and the low energy is these big waves, really big waves, and they're slow because they're big. But as you keep increasing, they get smaller and smaller, and then it becomes like a really tight curl. And these are high frequency. I will explain what these are in a coming slides. Okay, so wavelength. Let's tackle wavelength. Wavelength is a wave, and it is with the Greek letter lambda. So this, I wrote the word out so you guys can understand. This is lambda, and this is what is going to be referred as wavelength. So as the wavelengths get tighter, they're higher energy, and they will go on to, we'll start at low energy to high energy. And that's what you're seeing is that this one's not really representative of that, but it's showing you the wavelengths that we detect what these measurements are. So with the wavelength, it's we measure it from one point to the next same point on the next wave. So if we were to measure from here, then we measure this one. If we measure from here, then we measure this one. If we measure from here, then we measure, from here, then we measure the next one, or so forth, here to here, I think it is. So wherever it's the same exact point on the next wave is how we measure these. And we measure them in nanometers, which is what you see here. That's where you see them in the hundreds, it looks like. Or we measure them in meters, which is here. So these are in meters. But then when we look at visible, it's easier to do these in nanometers because you kind of get a better idea instead of saying 4.00 times 10 to the negative 7 or 4.00 times 10 to the, it's just easier by doing them in the hundreds. You kind of, if you hear the number and you understand the visible spectrum range, and you'll go, oh, okay, that's red. Oh, that's yellow, and so forth. So that's why. Again, this is another slide from one of my other books, and this gives a representation of what the waves look like with the increasing energy. So this is increasing energy, but this is increasing wavelength. You need to understand the terminology. Terminology is what's going to get you, and you're going to be very angry because a lot of students, and I love the confidence that intro chemistry students have, when they get something wrong, they immediately email me that there's something wrong. And 99% of the time, it's not true. I do make mistakes, but they usually read it wrong. They didn't pay attention to the units right. It's something that was student error, but they immediately, it's got to be my fault that they didn't do it right because they knew how to do the question. Not necessarily, you didn't read it right, you didn't translate it right, you didn't really pay attention to what was being asked. So terminology will save you a lot of problems. And I'm going to go over them. So this is just giving you a good representation. So basically, if it's increasing energy, you have smaller wavelengths. And if it's increasing wavelength, it's smaller energy, lower energy. So as a frequency increases, and the frequency is, let me explain what this is. It's a wave. So if you look at a wave, I think it's better if I can just show you. Let's go to here. Let's say I put a point. These are two. One is lower frequency. This is higher frequency. If I put like this fence here, I will get more smaller waves passing through a same amount of time than I will get here. So it's the frequency of how many waves can pass a certain point within a certain amount of area. That's what these mean. I can get more of these small waves passing in 10 seconds than I can get this one. That's what this means. So as in frequency increases, smaller waves, wavelength decreases. As frequency decreases, wavelength increases. So these are the terminologies that if you understand this, that's why I'm putting these slides to help. I'm a visual person. These help me understand what it is that's being said. Okay, so wavelengths of visible light. You can see here also, here is the waves for visible light. Lower energy, 700 to 400. And again, here, I found different thing, which gives a range. And your book is probably going to be a little bit off from these. They're generally in the same range, but for some reason the numbers just don't always add up, and I don't know why they can't keep it to the same numbers. But I wanted to show, see, like you can see this one goes to 400 and 450. This is 380 to 450. But violet is the highest energy, then blue, green, yellow, orange, and red is the lowest energy. And you can see with the waves how these look. I found this cool gift. This is not just a Pink Floyd symbol, if you know who Pink Floyd is. It is actually showing light that is being separated through a prism where you don't see them as waves, you see them as colors, but these are representations of the waves that are giving off in these colors. Remember I told you these are fingerprints, these numbers. So these are the waves that it would look like if you could see them. Okay, so describing electromagnetic waves. So I already showed the slide, but now we're going to cover it. So wavelength is the length of one wave. You measure one point to the next point. So if we measure, let's try to see if I measure here to here, then we can determine some information about that. Nanometers. For instance, the distance between these is going to be a lot bigger than the distance between these. So we can measure that in nanometers. Frequency is the number of waves per second, and it's the Greek letter nu, which really isn't a V. It's more like it does this like little hand wave hanging out but it's easier just to put V, or it's like this. The number of waves per second, it's the number of waves that pass a given point per second. So the units, so these are in nanometers or meters, lambda, and frequency is in the unit of inverse of seconds, which you can write it like this, or you can, in this means this. So this means 1 wave per second equals 1 hertz. So when you hear hertz, it actually means this, or 1 over S. So if I tell you I have 10,000 hertz, you should immediately know that those units actually mean this. It's 1 over S, or inverse of S. So they all mean the same thing. So if I have 500, I have 500, I have 500. They all mean the same exact units. Units are very important as you go into chemistry. Trust me when I tell you that in order for you to understand something, know what the units are. Density, if you know what mass is, if you know what volume is, these things can help you when you're having to do problems and you're stuck. Look at what the units are being presented. That's usually going to tell you what it is that they're giving you, even if you can't make sense of it at the time. Break things down in small steps. And the effort you make to understand the units that go with something will help you and save you a headache. So wavelength, know that wavelength, the units are nanometers or meters. Frequency, which is that little V. Know that the units are 1 over S with a subscript of -1, which is the inverse of seconds, or hertz. Any of those three will be given to you. They will not tell you it's always frequency. They'll give you the value, and you'll have to know. And how do you know? Look at the units. Okay, so describing electromagnetic waves. So again, if the wavelength decreases, the frequency increases, and vice versa. This is known as inversely related. Inversely is a very fancy word that will come up again when we do gases. Inversely means the opposite. So if one goes up, the other one has to go down. If the other one goes down, the other one has to go up. Why? Because we are now going to look at an equation here. C is representative of the speed of light equals wavelength times frequency. Now, speed of light has been determined to be 3.00 times 10 to the 8th meters per second. So that's what this number is. So if this number is set, then that means that these numbers have to fluctuate while this one is set. It doesn't change. So if this one doesn't change, these have to go up and down to make sure this always still balances out and this equals this. That's where the inverse comes in. Know the units. Know the units. Meters per second. Wavelength is meters. And frequency is 1 over seconds. So when these are multiplied, they have this. Know the speed of light this is a constant, so it never changes, meters per second. Frequency times wavelength equals a constant. See the speed of light. That's why these will always go up or down. This will always stay 3.00 times 10 to negative, 8, not negative. So let's do a problem. A beam of green light has a wavelength of 500 nanometers. What is the frequency of this light? This is where you're going to have to start getting comfortable with the symbols, know what they mean, know what they say, and what units go with them. I can't do this for you. You guys have to do this. I've always said I can give the class all the answers and you'll still fail chemistry, because if you don't learn it and I change one thing, you memorize is not learning it. Okay, so here is the formula, and we can solve for any of these depending on what we're looking for. So what is the frequency? So which one is these frequency? Well, C is the speed of light. It's a constant. This is wavelength. This is lambda. And frequency has to do with nu. So we're going to isolate that and solve for the frequency, which is nu, which means that the units, because I know what the units are, my units here should be 1 over S or hertz. When you know that, then you know how to set this up, and you know how, if you're catching yourself making a mistake. These are the things that I'm telling you to make a little extra effort to learn. Once you learn them, it does not become as difficult as it originally seems. So we can plug some of this in. So we take the speed of light, put that on top. We are given the wavelength. Now the problem is we're given the wavelength in nanometers. We can't use nanometers. We have to have them in meters. So 1 nanometer equals 10 to the negative 9 meters. So we can change this. I actually do not like how they changed this. I've done examples. I'm going to show you my examples later. Why? Because they didn't put a decimal here. So, but I get that they're trying to show it without the decimal. So 500 nanometers equals 500.10 to the negative 7 meters. Now, had they put a decimal point here, this would be negative 7. I don't like that they just left it, but it's 1 sig fig. The answer's in 1 sig fig, so I'm not going to give it a hard time. So this is a constant, so you would not consider it in sig figs. Okay, so now we plug everything in. The meter should cancel out because I already said that I know my units should be in 1/s or hertz. They do. I have my units. This is equality. And my answer is 6 times 10 to the 14 hertz, and that is the frequency. Okay, so let's go over something again here. Longer, if you have the red wave, is more oscillations. Excuse me, less oscillations, which means it takes longer to go through because the waves are bigger. Longer wavelength, lower frequency, lower energy. Those are the 3 things that go with a bigger wave. Shorter, a blue wave that is like a tight curl is a shorter wavelength, a higher frequency, and higher energy. So where are we going to, so this one we've already covered. We actually have not covered this one yet, and I'm going to cover it next. So the speed of light, you can solve for the wavelength. If you're asked for the wavelength, you can solve for the frequency if you're asked for the frequency, but know the units that come with that. Okay, so now we are on the energy of a photon. So an energy of a photon relates to the energy of a single photon. So your book gives this to you. I like to write it like this because this tends to help students more. So you're not going to see this in your book like this. But it helps if you learn it because you go, oh, photon, I know what formula I have to use instead of just with energy. So this relates to the energy of a single photon using the frequency. Why? Because we have energy, and this is in joules. Remember I told you the answers, you should know the units that go with the formulas. This is joules and only joules. This is Planck's constant. I'll come back to that in a second. This is frequency. What's frequency? Frequency is 1/s or hertz. So this is Planck's constant. It's named after Max Planck, which was a German physicist. He was a key figure in developing theories relating to light, energy, and structure. Planck's constant is the constant that connects the frequency to the energy of the photon. So this is another constant that doesn't change. The joule, J means joule. You will not get away from that. You'll continuously use joule. And it's joules times seconds. So this is one whole unit here. So wouldn't that make sense if frequency is 1/s? They cancel out and your energy is only 1 unit always, and it is joules. So now what if we're given, we solve for the speed of light, we have the wavelength, we solve for frequency. But we can actually plug in this prior formula if we needed to into this one. How? Because they both have frequency. So if we isolate for frequency, we can plug in the speed of light and the wavelength, and we can solve it all in one shot if we had the wavelength information. If not, then we would have to solve for frequency and plug it in. So in some cases, you can plug this entire thing in. In other cases, you'll have to solve for this one and then plug it in. Okay, so these are from another slide, but I want to give you an idea of how to understand how to read these. Arrange these 3 types of, because the wording can mess you up really easily. So these might seem a little confusing at first. Arrange these types of electromagnetic radiation in increasing wavelength. So first of all, what does increasing wavelength mean? That means lower energy. So you should end with the lowest energy item. Why? Because increasing wavelength, bigger wavelengths. So we're looking at things that are going this way. So if we do, we're given microwaves, we're given visible, and we're given X-rays. So if we're going in increasing wavelength, bigger wavelengths, that means that it's going to go from X-rays to visible to microwaves. This is the terminology that can mess people up. So X-rays have the shortest wavelength, visible light will be next, and microwaves have the longest wavelength. They have less frequency because they're bigger. This means the smallest amount of wavelengths to pass a set point in a specified amount of time because they are the largest wavelengths. Okay, let's look at another one. Arrange these 3 types of electromagnetic radiation in an order of increasing frequency. Now I put in parentheses to help you guys. Largest wavelength to smallest wavelength. So now we're going in the opposite direction. Frequency, lowest energy to highest energy. So the higher the frequency, it is the shorter the wavelength. That means more wavelengths will pass the set point with higher frequency. So microwaves have the longest wavelengths, less frequency. This means that's the smallest one. Then we go to visible, and then we go to X-rays. So more will have a higher frequency for X-rays than visible and microwaves. Arrange these types of electromagnetic radiation in order of increasing energy per photon. Energy per photon decreases with increasing wavelength, but increases with increasing frequency. The order in regards to energy per photon is the same as frequency. What does that mean? Well, we're looking at photons. If we go all the way to the back, to the front here, let's go here. Photons are, they're energy packets. So wouldn't you have more little energy packets in something with higher energy than lower energy? And something with higher energy, you would get more of in more frequency in something that is got on this side of the spectrum than this spectrum side. So it's energy packets. You will have more of them on here than over here, and you'll have higher energy over here than here. So a photon that is in this range has more more energy because it's higher energy on this side than on this side. So that's what this means. So you would look at frequency. Microwaves have the longest wavelength, so you're gonna have less frequency, you're gonna have less energy per photon than visible light, and then X-rays. So this means that also X-rays have the highest energy per photon because it's in this range. Okay, so example of a photon energy. A photon has a frequency of 7.50 times 10 to the 14 hertz. What is the wavelength of this light? What is the color of this light? What is the energy of the photon? This sounds really complicated. It's not. You just may have to do more steps, but it's not that difficult. So this is the formula you can use, giving you frequency. So we have frequency. We have this one, which we need, we have a frequency. A photon has a frequency. So we're given the frequency here, but we don't have the wavelength. So we need the wavelength. The wavelength tells us what color range this is in. This is nanometers. Remember, wavelengths do nanometers or meters. So we're going to isolate wavelength, speed of light. We're going to set this up, which we do, and we cancel out the units. My wavelength should be in meters because that's how I set these up. So once I set them up, we have 3 sig figs. We don't look at the constant one. This ends up with 4.00 times 10 to the negative 7 meters. It's really easy to put this in nanometers, and I will show you a conversion on one of my own problems. So if I tell you this, it's a little confusing. If I tell you 400 nanometers and give you the scale, you can tell that this is in the violet range. So this is violet. Now, the next one is asking for what is the energy of the photon. That's where I had put something like this because it helps you remember it easier than something like this. But they're both the same. It's just sometimes putting that photon helps students remember it. So we put that here. Here is our formula. So we take the E equals, now this should end in joules. If I don't get an answer that ends in joules, that could be an indication that I didn't do this problem correctly. So we take our Planck's constant, which is 6.63 times 10 to the negative 34 joules seconds, and we take our value, which is here, which is the frequency, and plug that in. My seconds should cancel out. It does, and it gives me an energy, the energy of the photon is 4.97 times 10 to the negative 19 joules. So I did this in 2 steps, technically 3, because I converted, well, I didn't. The slide converted this to nanometers, and I was able to tell what color it is. Okay, so now I'm going to give you a similar problem, just like the one, but I worked this out. Okay, so what is the wavelength in nanometers? We're given a frequency of, I thought it was the same for a second, 7.23 times 10 to the 14 hertz. Frequency, that means that hertz is 1 over s. So what is the wavelength? I'm giving the formula and the speed of light. So the first thing I have to do, I know this seems like a really busy slide. I boxed everything in, but I kept it on the same page so you can see where some of these answers are. So the first thing I do is I solve for the wavelength. That's very similar to the slide that I showed you. I put the speed of light. I changed the frequency of the hertz, so 1 over s. The seconds cancel out. It gives me meters. Now, I did something that I never do. I actually put the whole number from my calculator. I didn't put it in scientific notation. I left it. Why? Because I can't use it. I need to know what nanometers. This is specifically asking for in nanometers. So I know the conversion is 1 nanometer equals 10 times negative 9 meters. So I set that up. I have meters here. 1 times 10 to the negative 9 meters equals 1 nanometer. These cancel out. This gives me, again, I left all my numbers, is 414.937 nanometers. And so let's take a look at this first problem. This is 3 sig figs. So this is a 9. So this is 415 nanometers. So that's what this is here. So if we jump down here, we can look and see it's about here. So it's about purple. I know I don't like that they didn't really specify and show clearly that this is purple or violet, but that's what this is. And then they call it purple when the other page calls it violet. So there's a little few weird inconsistencies. And if I had caught that, I would have changed this before right now. Because on the prior page, they put violet. So this is actually violet, purple. They mean the same thing in a sense. Okay, so you see this. Now, what is the energy? So what is the energy? Where does the energy come from? Well, E represents energy, so it's actually asking for a photon. It's not always stating that. That's where this comes in. The energy is in joules, so my answer has to be in joules, but there's no other formulas that I've given you that represent energy. So when you see energy, that's what this is. We know what Planck's constant is. So I have the frequency. Plug all this in. So in this case, I didn't have to do it like this. I could have actually did it 2 ways. I did it the harder way. You could have just plugged in frequency and multiplied it by this, and you would have gotten the answer. But because I had the nanometers, and sometimes you have to do things in 2 steps, I left my wavelength. So again, here's your frequency, which is new. You would have just times Planck's constant by this number, and it would have given you an answer. But that's not how chemistry works. Chemistry usually makes you do multiple steps. So I did it the harder way, which is, let's go back if I can find it. I solved it with this one because I already had the wavelength. So I solved it plugging in speed of light and the wavelength, and it gave me this number. So depending on what, you should get the same number. So that's not the issue here, but I made it a little harder so you can see how I carried it over. So here's Planck's constant, speed of light, wavelength. So here's Planck's constant, speed of light, and I left my number from here. I did not round and use this one because when you have to do a problem with multiple steps, you don't round until the very end. So I left it on purpose. My meters cancel out, my seconds cancel out. It leaves me an answer of 4.79 times 10 to the negative 19 joules. And that's what you get here. So this is representative of how to do a problem that is something similar to what you should be getting. It's not difficult. There are steps to it. Understand the units and you will not go wrong. Okay, so find the frequency and the energy of a photon of light with the wavelength of 723 nanometers. So we're given some of the information. I added photon on there so you can see that. Okay, so what do we need to do? First thing we need to do is convert nanometers to meters. Second thing we need to solve for frequency. And the third is we need to solve for the energy of the photon. We don't necessarily have to solve for the frequency because we have the wavelength. We can plug all that in. But it depends on how you want to do it. In this case, I did plug in the frequency since I solved for the frequency. And you didn't really have to, again, because you're given the wavelength, you could have just kept the meter, kept this and plugged it in with the way that I did this one. I hope you guys are understanding. You can use this one or this one. So with this problem, once I got the wavelength and converted it to meters, I could have used this one. I didn't. I solved for frequency and then used this one. Why? Because when you understand how to do a problem, then you understand you have different options on how to do something. And you should feel comfortable knowing that you can change some of the stuff. And I wanted to show you a different way to do it. Okay, so here is my information I need. So in the first thing, I convert 723 nanometers to meters. I give you the conversion factor right there. You can see it's boxed in. I have my 7.23 times 10 to the negative 7 meters. Now I could have used my wavelength and used it solving the way I did the previous problem, but I didn't. So I now take my frequency because I isolate this away and I end up with this. Now, had it just been asking for this number here, I would have rounded this and the answer would have been 4.15 times 10 to the 14 hertz. But I'm not. I needed this to plug in to use it on this problem. And that's what I did. So here's my Planck's constant, My nu, which is my frequency, I added that here. I didn't round it, but I always put a little line to show where it should end. And my value is 2.75 times 10 to the negative 19 joules. Energy should be 1 unit, and it's joules. Okay, so which wave has the highest frequency? It should be really easy. You don't even need to look at the numbers. Look at the waves themselves. Highest frequency is highest energy, means more waves will pass through one unit, one gate, one fence, whatever, one point, and that's going to be C. And the highest energy is actually in the 400 range, where red is in the 600 to 700 range. It's kind of the opposite. The lower number means a higher energy for the visible, and the higher number means lower energy. Okay, so which of these does not describe a photon of light with the wavelength? I didn't solve this one for you. I'm going to tell you what the right answer is, and I'm going to tell you how to break it down. But this is very similar to the other problems that I just showed you how to do. Okay, so what does this mean? I'm going to give you the answer. We have, which of these does not describe a photon of light? So that means that you have to use this one, but you're given a wavelength of this one. So basically what you could do is convert this to meters and then the speed of light and plug it in. Well, you can either do it this way. You can plug in for here and get the frequency and times it, or you can use that equation where you solve for, you isolate frequency and you plug these in. Okay, that's going to tell you what the answer is. So what the answer is, then you can start seeing which one the answer is not. So first things first, 685 nanometers. If we look here, it's in the between the red range. So this is a true answer. That applies. We're not worried about that one. 685 nanometers. If we didn't put a decimal, this is actually true. This is just a different conversion without the decimal, which bothers me. And now, if you plug in for frequency, you're going to get this as your frequency. You're going to get B. So the only one that doesn't apply, because if you plug in all the answers, you're not going to get this as your answers for energy. C is the one that's wrong. And this is one that is a very tricky one if you're first learning this, because you don't always understand what all this information is giving you. You have to make the effort and just plug things in until you can start seeing what it is that you're understanding, you're looking at. What I'm saying may not make sense, but chemistry problems can be very confusing. And sometimes you have to keep working at them until you start, something will click and go, okay, I get now what they're asking. All right, so which transition produces light with a frequency of 6.17 times 10 to 14 hertz? I don't like this problem, but they gave it to me because we haven't covered transitions yet. So you don't even know what transitions yet. What these mean as these are levels, and when they give off energy, they give off energy in these colors. And depending on, one goes from 6 to 2, 5. So think of these as stairs, levels. Goes from 6 down to 2, 5 down to 2, 4 down to 2. So when they give off this energy, they give them off. So we want to know, with the frequency of this, which of these transitions is produced. So how would we do that? Well, we use this formula. So we plug in and we solve for the wavelength, because the wavelength right here tells you what color it is. So I didn't solve this one for you. I'm just going to tell you what the answer is. So the answer is B to 4 to 2. So where is that? That would be, it's going to be 4 to 2. So it's going to be light blue. So that tells me that my number, when I plug in and I solve for the wavelength, it's going to be in this range here, which is going to be about 450 to 500. And that's what I should get in nanometers as my answer. And that's going to tell me that it's this. Because so basically solve using this equation, you're given the frequency, you're going to be given a value. That value should be here. It's going to be here because it's between 500 and 400. And once you see that, you go to light blue, it's 4 to 2. That's the answer. So hopefully that makes sense. Okay, summary of electromagnetic waves. Light is a form of electromagnetic radiation. It's described as frequency, wavelength, and energy. You should definitely know the units. The units will save you. We use a formula of using the speed of light, and we use one with energy with Planck's constant, and there's two different versions that we can plug in.